What do your favorite video game and that app you use to order lunch have in common? Well, deep down at their core, they both rely on a really simple but incredibly powerful idea, repeating an action over and over. Today, we're going to dive into programming's ultimate power tool for automation, the loop. So, to really get why loops are so critical, let's tackle a real-world problem. Imagine you invest $10,000 in an account that earns 5% interest every year. The big question is, how many years is it going to take to double your money? I mean, we could sit here and calculate it year by year by year, but that is exactly the kind of repetitive chore a computer was born to do. Okay, so how would a computer even approach this without a loop? Well, it would have to follow a set of instructions, one by one, over and over again. Let's take a look at what that manual process feels like. Right, so here's the manual algorithm. We start at year 0 with our 10 grand. Then we add a year, figure out the interest, add that interest to the balance, and then, and here's the key part, we have to ask ourselves, have we hit our $20,000 goal yet? If the answer is no, we got to go all the way back to the beginning and do it all over again. And again, you can see how this would get old fast. You can already feel the grind, can't you? Just imagine doing this for a much bigger investment, or maybe a more complicated calculation. Manually repeating these steps is just so inefficient, and let's be honest, it's not what computers are for. There just has to be a better way. And here it is. The elegant solution to our repetitive problem is a programming structure called the while loop. It is designed specifically to automate this kind of grind for us. So what is a loop, really? Well, at its core, it's just a way to tell the computer, hey, see this block of instructions, do it over and over and over again. It's the tool that transforms that tedious manual process we just walked through into something automatic and unbelievably efficient. And this just illustrates the magic perfectly. On the left, you've got our manual steps. On the right, you have the Python code for a while loop. See how perfectly they map to each other? The phrase repeat while balance is low literally becomes the command while balance less than 20,000. And all those steps we wanted to repeat, they're just tucked right underneath it. The loop handles all that repetition for us. It's beautiful. So let's break this down because every while loop really has 3 key parts. First, you've got the initialization. That's where you set up your starting variables before the loop even begins. Second is the condition. Think of this as the gatekeeper. The loop will only run while this condition is true. And third, the update. Somewhere inside that loop, you have to change something that affects the condition. You have to move it closer to becoming false so the loop will eventually, stop. So the while loop is perfect for when you don't know exactly how many times you'll need to repeat something, like our investment problem. But what if you do know? What if you need to do something exactly 10 times? Well, for that, we've got another tool in our toolkit. So what if your task is a bit simpler? Let's say you just want to print the numbers from 1 to 10. You know you need to repeat that print action exactly 10 times. This is what we call a count-controlled or a definite loop. And yep, there's a loop designed just for this situation. Check this out. On the left, that's how you'd print numbers 1 to 10 with a while loop. You have to set up the variable I, check the condition every time, and, this is the important part, you have to remember to update I yourself. On the right, though, is the for loop. It is so much cleaner. That one line, for I in range 1 to 11, handles all of that setup and updating for you, automatically. It's just more concise and way less likely to cause errors. And the power of loops goes way, way beyond our first example. You can use them to add up a whole series of values, find averages, count how many things match a certain criteria, find the biggest or smallest number in a huge data set, or even process every single character in a book. They really are the workhorses of data processing. But with all this power, it's also kind of easy to make a few mistakes. You know what they say? With great power comes great responsibility. And a few classic traps. When you're dealing with all this repetition, it's actually pretty easy to make a couple of common mistakes. So let's talk about how to navigate these dangers. This has to be my favorite analogy for the first major trap, the infinite loop. The source material just puts it perfectly. If your loop's condition never becomes false, your program gets stuck on a treadmill, running forever, and you literally have to pull the plug to shut it down. And here is a classic example of that. We start with the year at 20. The loop continues as long as year is greater than 0. But look at the update step inside the loop. Year equals year plus 1. We're increasing the year. It's always going to be greater than 0, so the condition will never ever be false. And that's a one-way ticket to an infinite loop. All right, the next beast is a little more subtle, the off by 1 error. It's that nagging feeling you get when your loop runs one too many times, or maybe one too few. In our investment problem, should we have started our year counter at 0 or at 1? Getting this wrong can throw your entire result off.
So how do you defeat this little goblin? You don't guess. The absolute best weapon is a simple test case combined with this really powerful debugging technique called hand tracing, where you basically pretend to be the computer and walk through the code step by step.
Okay, let's trace a simplified problem together, doubling $100 at 50% interest. We start with year at 0 and the balance at 100. Is 100 less than 200? Yes, it is. So we enter the loop. After that first pass, year becomes 1 and the balance is now $150. Is the condition still true? Yep. So after the second pass, year becomes 2 and the balance hits $225. Now, is 225 less than 200? No, it's false. The loop stops. The final answer is 2 years. See? Because the loop had to run twice to get us to year 2, we know for sure that the counter had to start at 0. Hand tracing proves it. So now that we've mastered the mechanics and we know how to avoid the traps, let's just step back and look at the big picture for a second. What does mastering loops actually unlock for you? What can you do with this? So much. You can process huge text files, you can validate that a user actually typed in a correct phone number, you can run complex scientific simulations, you can generate graphics by looping through every single pixel on a screen, build beautifully formatted data tables, and power the core mechanics of video games that need to update the screen over and over again. But as you start building all these amazing things, you are going to run into errors. Programmers call them bugs. And don't worry, it's a rite of passage. In fact, there's a legend that the very first computer bug was a literal bug. A moth got stuck in a relay switch at Harvard and gummed up the works. The computer pioneer Morris Wilks realized this way back in the day. He said, quote, "A great part of my future life would be spent finding mistakes in my own programs." Finding and fixing bugs isn't a sign that you've failed. It's just a fundamental, normal part of creating things with code. So let's bring it all home. What's the one thing to take away from all of this? It's that loops are your key to unlocking a computer's main strength, performing millions or even billions of operations without getting tired and without making mistakes. They give you the power of massive repetition. And that brings us to the final question for you. Think about your own work or your hobbies. Now that you have this power, now that you understand how to automate the grind, what's the first repetitive, boring task that you're going to teach your computer to do for you?